Okay, so thank you, thank you everyone for organizing the safe space, and I really mean that. It's amazing to be here, and also I would just like to start with a very short story how the goal of this, so the visibility is already improving, because whenever I apply to go to a conference, at my faculty, there's all those questions. So why are there categories important, or why do you want to go there? What's so fun about it? And like for the first time ever, there were no questions about maths. Like, honest to God, my boss asked me, so what's important about this queer stuff? What is fun about this queer stuff? And like, I said I would gladly draw some commutative diagrams. What's fun about queer stuff? And like, apparently it worked, because he let me come here. Okay, so I would like to start by inspiration, because it's important. Oh, sorry. This is joint work with Marco Rampazzo, from University of Bologna at the moment, like I think for a while at least. Okay, so I'm going to start by inspiration, and this is like very down-to-earth talk. Like, I mean, I'm going to be talking about a very specific object here, so it's not really general. So inspiration is as follows. So if Y is an honest-to-God resolution of singularities, so like honest to God, we know it exists by Hironaka and so on. Then we have the following functors. Yes, we have, so this is pi, obviously. So we have the push forward from dby to dby, and the derived stuff was mentioned so many times that I don't feel forced to define it during this conference. And the pullback from dperf y to dby tilde, we have the following functors, which are mutually adjoint, yes, where perf means perfect complexes. And if the singularities are rational, then the composition of those two functors is the isomorphic to identity functor, and so on and so on. And this is like coming from geometry. And then, like, for example, Kuznetsov says, okay, so like, we always have resolution, but for example, we not always have a Krepin resolution or whatever. And maybe instead of looking at geometry, let's stick to the level of categories, yes? And so we have this definition of a categorical resolution of singularities. And a categorical resolution of singularities is a smooth, triangulated category, fancy D, and the pair of functors. And as I have not much time, I will, wave hands a little bit, that emulate the behavior above, yeah? So instead of looking at the like honest-to-God geometric resolution of singularities and see what happens at the level of categories, so let's say, okay, let's turn this around, yeah? The resolution of singularities will be some other smooth category, whatever the hell a smooth category is, and the pair of functors that emulates this, yes? So in that way, we can look at the resolution of singularities from the higher point of view, and we get some nice results. For example, we can define, well, Kuznetsov can, and some other smart people, smarter than I am, can define like Krepin resolution of singularities and so on and so on. And for example, there are situations when we do not have the geometric Krepin resolution of singularities, but yet we can find the categorical one. So there is like some nice natural generalization. And continuing with the inspiration, in 2008, Kuznetsov stated the following conjecture, that if Y is a cubic fourfold, then Y is rational if and only if the AY, well, we can call it Kuznetsov component because he's not here. Then the Kuznetsov component defined, which I will define in a moment, if Kuznetsov component is equivalent to a derived category of a K-free surface. So this is his conjecture from his wonderful paper from '08, and he like goes through the examples of that support this conjecture. What is AY? So if we have a, so basically this is okay. So maybe what is AY? So if dBy is the semi-orthogonal decomposition of the category of cubic fourfold, then AY is defined, well, as usual, yeah, as the guy that's orthogonal to the rest. Yeah, so there are no arrows going from AY to the, from the right stuff to the left. Yeah, there are no arrows going from right to the left. Conjecture, cubic fourfold is rational if and only if this guy, this guy is equivalent to the derived category of a K-free surface. And okay, this is visible. And for example, there is a case of nodal cubic fourfold. Wonderfully worked out. So, okay, maybe more drawing. Okay, so if we take a nodal cubic fourfold and we blow up the singular point, so like in a standard thing, yeah, we blow up the singular point. Over it, we get a smooth quadric of dimension 3. Yeah, this is fourfold, this is dimension 3. Yeah, and so this is the exceptional divisor over the singular point. This lives nicely in the blown up nodal cubic fourfold. Then we can actually take the other projection. Yes, we can think at we can look at this resolution of singularities. We can project it to P4, and what it turns out, actually, we see that this guy is the blow up of a P4 in a K-free surface. Yes, this is a blow up of a P4 in a K-free surface. This K-free surface. Okay, so like if I have a nodal. This is 0 F2 plus F3. So if my variables go from Z0 to Z, I mean P4. So I mean P5. Yeah. So if my variables go from Z0 to Z5, then I can think about a nodal cubic fourfold defined like that. Yeah. So in F2 and in F3, Z0 does not exist. Yes. Locally, this is smooth degree 2 something. So basically, S would be the intersection of F2 and F3 in P4. Yeah, so this is a K-free surface by the adjunction formula, for example. And so we have two blow-ups of, well, two ways of describe the Y tilde. Yes, and like taking a cue from John Mitchell, we look at Y from both sides now, and we look at the derived category of Y of Y tilde, sorry, in two ways, yeah? So very quickly, okay. Pi, this? I'm just projecting, it's projection from the node. Well, after, blow up and, yeah, and projection, yeah? So we can look at the category, the derived category of Y in two ways. So on one hand, dBy tilde is this. Yeah, so this is left-hand side. This is stuff coming from the exceptional divisor, and this is, well, this is basically coming from it, yeah, from this guy. But from the right-hand side, by Orlov blow-up formula, for example, we know that dBy is this. sorry, of course, this is P4, yeah? Yeah, of course. Oh. And the answers will reveal the depths of my ignorance. So it's oh, so this is when we, this is the semi-orthogonal decomposition of the drive category. This is how we write that.
Okay,
so like someone mentioned semi-orthogonal, it was mentioned a few times already, so I assumed if they got away with it, I would. Without defining what the semi-orthogonal decomposition is. Like basically, we take the drive category of something and like the arrows only go one way, so you can think about this. Like this generates the triangulate category. These are like full triangulated subcategories, and the arrows go only one way. Yes, and also the arrows only go one way, and there's.
So the order matters.
Yeah, the order matters.
So let's say I ask a question like, why don't you include O of 3H?
Well, because it's already there. Yes, it's there. We can just Can we because this would take long? Can we move it to the after party? Yeah, it is there. These are standard results. Yes, they're standard for people who do that. Yeah. Okay, so okay, let me get back to this. So we can look at this drive category in two ways because and the wonderful part of this paper, the wonderful result, the inspiring one, is that actually AY is equivalent to this phi of dBs. So this is not obvious, yes, but well, when we have the two semi-orthogonal decompositions of the same category, we hope to find, for example, mutation that takes us from one to the other. And in this work, there are explicitly given mutations that show that this guy is this guy. Well, they are equivalent. This guy is this guy. So in this case, we know what this component, which up to yesterday, but as Tyler nicely pointed out to me, this is known and this is computable just in other ways that we've been trying to do it. But up to yesterday, I believe it was difficult to find. So thank you, Tyler. Knowing what this component is a big part of fun, yes? So we don't know what this, we know this component exists, yes? Because this component is defined in a very, non-explicit way, yes? I want it to be orthogonal to the rest, yes? So this is given by by definition. And here, we can find it very, very geometrically, yes? So we can find it that this is the derived category, well, this is equivalent to the derived category of the K-free surface. And so that was the Kuznetsov's work from 2008. And then a few years later, it was even more precisely refined. So 23, and I'm extremely sorry if I mispronounce names of the people. So Kapani, Giovanzana, Liu, Magni, Martivelli, Petruzzi, and Song. They have this wonderful theorem that the kernel of dBs to AY, no tilde involved, yes, because dBs and AY tilde, this is the same guy. But then this guy goes to AY, yes? This is the resolution of singularities at the level of AY. So there is some kernel. And the kernel of this is classically generated by T push forward of queer S, where T straight S, so this is straight S, sorry, is the inclusion of K3 into Q, and queer S is the spinor bundle on Q. Yeah. So not only we know what this Kuznetsov component looks like, we also know what, well, thanks to them, we also know what dies. Yes, what dies from the resolution of singularities to the to the singular guy. So this is like a very, very nice, explicit, geometric description of what's happening there. Yeah, it's like this is pure magic, right? You can see the geometry like underneath it, not behind it, but underneath it. Yes. So this is the inspiration. And so what's the next step after cubic fourfold? Yes, of course, nodal Gushel-Mukai fourfold, right? This is out of the question. Yeah. So we are trying to do, and we are like close to finishing it. We are trying to do similar stuff for nodal Gushel-Mukai fourfold. So let's say our case. Okay, title. Yeah. So no. Q is the quadric. Yeah, it's the exceptional divisor. Yeah. So on the quadrics we have spinor bundles. This is three-dimensional quadric. So one spinor bundle, we know which one it is. Okay. So let XP be a nodal Gushel-Mukai fourfold. So what is it? Okay, so we can think of XP as the intersection of a G25 with a hyperplane with a nodal quadric. So this everything lives in P9. Yes, this lives in P9. G25 lives in P9, intersect with a hyperplane, intersect with a nodal quadric. Of course, we want this node to live on this hyperplane and live on this Grassmannian. So this node is, well, it doesn't appear because of tangency or whatever. This node, like honest to God, we put a nodal quadric there, and the node survives on the X, of course. Then we have a following diagram, yes? Okay, so now the picture is gonna be huge. I should squeeze it here. Okay, so, or maybe not. Oh. I will first draw a picture, then I will explain what is what. Yes, key. Bon. Okay, K is not important, PQ. Okay, so we have a following picture. Maybe instead of writing what is what, I will explain it a little bit and then prove some stuff. So this is our nodal Gushel-Mukai fourfold. So this is the equivalent of YP. Now we blow it up. Honest to God, we blow it up. We have something with a quadric living inside. And now we have another projection. So now we're projecting to P7. Why P7? Because of course this lives in P9, but since we're intersecting with H is a P8 in P9, so we can think about XP as living in P8. Yes, so we're projecting from P8 to P7. Now T, and you have to believe me on that, is the intersection of three quadrics. And by abuse of notation, I will write this as intersection of QP. QP is the guy living upstairs, but again, this is a nodal quadric, so I can ignore. So nodal quadric can be written as something without one variable. After projection, the equation is exactly the same, but now it's a smooth quadric downstairs, yes? So T is an intersection of three quadrics. And, oh, I'm out of time. Jeez. So inside that, there is a P4. Inside that, there is a P4. So those first two quadrics like intersect slightly more than they should. And now what are we doing? We are blowing P7 in P4. We are blowing up the P7 in P4. And we're getting a P5 fibration over P2. Yes, we're getting a P5 fibration over P2. Each P5 is basically geometrically responsible. Oh, and by the way, this construction is inspired by Kapustka, Bini. Yeah, this is from their paper. So this is inspired by their work. So we blow up the P7 and P4, we get P5 fibration over P2, and each fiber is like a P5 containing this P4, sort of. And now, what happens with those quadrics? Those quadrics contain this P4. So if so I intersect this quadric with P5, I get a four-dimensional quadric. A four-dimensional quadric containing P4. So there is only one option. This quadric is reducible, right? So those quadrics become a intersection of two P4s, yes? So one P4 is the one that we're projecting from. The other P4 survives in the fiber just as a P4. So intersection of those two guys in the fiber is intersection of P4 and P4 in P5, which is a P3. So we have a P3 fibration over P2, and then we intersect with one more quadric. This quadric now intersects it nicely. So we have a quadric fibration over P2. So R, quadric fibration over P2. Yes, R now is a quadric fibration over P2, and this guy and this guy are birational. Yes, they are birational. So we have, so this is like one step further, one step more difficult than this, because here we have two descriptions of the same guy, Here we don't have two descriptions of the same guy. We have birationality between two guys, yes? And this is quadric fibration. Fibers are two-dimensional quadrics, yes? So now, what is this? S is the, well, basically S is a cone over P1 cross P2 intersected with hyperplane section intersected with Q. So this is a surface. And this is what we see. These are basically the lines passing through the node that are contracted. This is, well, you can think about some surface. This is a P1 fibration over gamma. Here, S hat is another P1 fibration over gamma. Gamma is the degree 6 curve. Degree 6 curve. So you probably see where it's going to, yeah? So now, what is this? What is the upper part of the picture? So the upper part of the picture is the Mukai flop. And let's say lemma. Oh, thanks. Lemma. This guy is a simple K equivalence. In particular, so with, in particular, it is, well, it is a resolution of this, of the indeterminacy locus of this birationality, right? And F is a P1 bundle over S and over S hat, and locally trivial P1 cross P1 fibration over gamma. Yes, so we have a P1 fibration over gamma, P1 fibration the other way over gamma. So this is a P1 cross P1 fibration over gamma. We contract one P1s, we get S. We contract other P1s, we get S hat. So this is basically the whole story on the exceptional divisor, so to say. And now the only thing that's left is actually see, how the derived category of this and this relate to each other. Because like if this is a K equivalence and this stuff is birational, in this case, this implies the derived equivalence. So from this, we know that dB x tilde is equivalent to dBr, and okay. Okay, sorry, too many boards. In particular, okay, I'm over time already. So maybe just quickly. So we can write dBr. This is again from Kuznetsov because this is quadric fibration. This is, I promise this is the last board. and db x tilde as quite similarly to the cubic fourfold case. So U dual is the dual to the universal, is coming from the Grassmannian, yes, universal bundle of the Grassmannian. H's are hyperplane sections. Zeta is the, sorry, psi is the relative of one of the fibration. And B, okay, B is the monster. B is a dBp2 B0, so this is derived category of B0 modules of a Clifford algebra, and please don't ask me what it is. And these are the derived categories of those guys, and we have explicit mutation as a subcategories of this bigger X, of this common, you know, of the guy living over them. And so we have this, we have equivalence of this, but and we can show that they are equivalent, everything works, but so far we are unable to see where this guy goes exactly. And our hope slash goal is this, that B is actually equivalent to AY tilde, yes? That would be the equivalent statement to this one, yeah? This is what we're trying to get. We're trying to whatever. We're trying to show that this guy goes to this guy. But actually, this is slightly more complicated because than this case. Because first of all, we have this equivalence, which we have, but then also after that, we should see the mutations inside one of the categories. Yes, so there's like more work to be done. But actually, yesterday's talk with Taylor got me hopeful about, you know, other approach to that problem, or like equivalent approach to the problem. So maybe this will happen. But yeah, basically this is what we're trying to do. Yes, we are trying to mimic, or, you know, like find analogous thing to this wonderful geometric description of the Kuznetsov component of this resolution of singularities, and maybe even find the kernel. There is some more stuff happening on fibers, but honest to God, I have no time to talk about it. But yeah, basically this is where we are, and this is wonderful birational thing. And this is what we're trying to get, and hopefully it's like, you know, we're 5 minutes away from it, just the correct 5 minutes away from it. Okay, so thank you very much.